you consider the general transport equation, there are 4 different types of terms. One is the unsteady term, another is the advection term, another is the diffusion term, and another is the source term or generation term. So, we have seen so far problems or scenarios where you could have the unsteady term, the diffusion term and the source term. One classical example that we have covered is unsteady heat conduction equation, but that did not have any fluid flow. So, advection, which physically comes from the acceleration of the fluid, that will bring in the transport of the physical variable via the flow of fluid. Like if you have heat transfer, then heat can get transported with the fluid flow from one place to another place. Although we loosely call it as convection, this is fundamentally known as advection, and advection plus conduction is known as convection. So, convection cannot take place without conduction, like heat transfer. Similarly, you have mass transfer, etc. So, why convection cannot take place without conduction? Let us say you have a hot wall on which a fluid is flowing. So, how can the heat get transferred from the hot wall to the fluid? That is only by conduction, and then from there it will be transported within the fluid by both conduction and advection. So, in that way conduction is a must for such a scenario where fluid flow is influencing the transport of heat and very similar other applications. So, overall the scenario is you have convection because you have fluid flow, and you anyway also have diffusion. Diffusion of heat is conduction. So, in that way in a general terminology, this is called as convection diffusion problem. This is just a name. So, what we will now see that in the convection diffusion problem, we will add the fluid flow effects, and when we add the fluid flow effects, what is the implication in your solution. So, when you add the fluid flow effects, the question is how do you know what is the velocity, because let us say you are solving the energy equation where the convective transport of heat is taking place. So, what does it mean? That you have a change in temperature where the fluid velocity also plays a role. So, if you are solving or trying to solve for temperature from such an equation, you have to substitute the value of velocity, only then you can solve for temperature in that equation. So, question is where from that velocity will come. So, that is what is the numerical solution of the fluid flow equations that we will study in the next session, but for this session we will assume that it is known from somewhere. So, if it is known from somewhere, then how can we use that to solve for other variables like say temperature for example. So, let one such variable be phi. So, whatever we had the previous example where we were talking about the diffusion problem, the temperature and thermal conductivity, those are sort of generically replaced with some variable phi and some diffusion coefficient gamma, and that means that you can cast the general equation, and we have seen that how this can be derived from the basic conservation principle, that we can cast the equation in this form, and the velocity is of course to be solved from the continuity and the momentum equations, and we will assume that they are solved, and therefore, in the equation which is written in the box velocity is known. So, the problem that we are trying to address is if u, j they are known, then how to solve for phi. Okay. Now, any problem, as we discussed, that any problem to understand it fundamentally, it is always good to start with one dimensional. sometimes it may appear that one dimensional is too simple, but if you are looking at fluxes. So, you have a surface and flux is always normal to the surface, that means the flux gives a local one dimensional effect of what is happening, although overall it is 3 dimensional in general. So, if we understand the one dimensional problem and from that we understand how to treat the fluxes, that concept we can readily extend to 2D and 3D. So, as usual we have constructed a control volume, the nomenclature is exactly the same what we used for the diffusion problem. So, one dimensional version of this means you have only x direction and steady. Unsteady we are not bringing it here, because unsteady term, how to treat it, whatever we have discussed for the diffusion type of problem, it is same for all types of problem. That is, you have those explicit, implicit, Crank-Nicolson, those types of schemes. So, that is not dependent on whether advection is there or not. So, we have not kept the unsteady and we have also not kept the source term, because source term how to discretize it we have seen, again that does not depend on whether it is fluid flow problem or not. So, what special feature we have added is that had there been no fluid flow, the left hand side would have been 0. Now, you have a left hand side ddx of rho u phi. Okay. So, once you have that, of course, this is such an equation which has analytical solution. Anyone who is looking into this will argue that if this has an analytical solution, why are you talking about it for a numerical solution? Now, this is where you have to develop your maturity of how a subject is developed. Always when you develop a subject, you try to standardize it with respect to something for which you have a very comprehensive knowledge in hand. So, this particular scenario, although it looks like a very simple scenario, it will enable you to standardize the algorithm, which you can extend it to more complex scenario where you do not have such a simple one dimensional equation. And the continuity equation also along x, if you have that, you will have ddx of rho u equal to 0. There is no y or z variation. So, now with this we will try to see that if we want to discretize it, so what we would do. So, look into the previous slide. So, what would you do? Your step is, the step 1 is integrate the governing differential equation over the finite control volume. This is the first step of the finite volume method. So, if you integrate this ddx and then dx and integrate it, that means d of rho u phi, integrate from small w to small e, then what you get? Rho u phi at small e minus rho u phi at small w. Right hand side is diffusion, and in fact for diffusion we have seen how to treat it, and that is where we start with our first sort of scheme or first method of discretization. So, we have used this piecewise linear interpolation for the diffusion terms for our diffusion problems. So, if you recall, for the diffusion problems we assume that phi varies, or in that specific example temperature varies linearly between two grid points, and that is what we have drawn here. So, in that case the right hand side is just a difference equation, because if it is linear, it is d phi dx is phi p minus phi w divided by x p minus x w, that is delta x e. So, in that way right hand side you can write, and although it is a linear interpolation, in terms of finite difference it is just like something which we call as a central difference scheme. So, in what we are trying to do here, and in fact this is something which is quite interesting, that when we are talking about the central difference, forward difference, backward difference, etc., in finite difference, they are all different linear forms of interpolation, only between which two points you are interpolating, accordingly you will have the name of the scheme. So, in a way whatever is the method, either directly or indirectly you are approximating the function by another function, in this case a polynomial linear polynomial. Now, the main focus here is the left hand side, because this has now appeared as new to this problem. So, if you have this say small e at the midway between capital P and capital E and it is linear, then phi at small e is half of phi at capital E plus phi at capital P, right, because it is a linear variation, and similarly phi at small w. So, that is what we have written, because our objective is that in your left hand side expression small e and small w values are coming, but your variables which you are solving are based on the main grid points, that is capital P, capital E, capital W, etc. So, that requires interpolation, and here what we are doing is whatever profile we have used for the diffusion term, the same we are using for the this so called convection and putting up that interpolated value. So, you will get then again of the same form AP into phi P equal to AE into phi E plus AW into phi W. See, that is why I emphasize so much on learning how to solve the system of linear algebraic equations, because you will get a similar system no matter whether your fluid flow is there or not, only coefficients will change. So, you have these coefficients AP, AE, AW, etc. So, one very obvious observation that you can see, that if u is positive along the x direction, then AW, so we have assumed that delta x E and delta x W are all the same, and that is equal to delta x, just to write simplified form. So, you have AW, it is positive because all other things are positive. So, by one of the basic rules all coefficients should be of the same sign, but AE there is no guarantee that it will be positive. So, it all depends on whether gamma by delta x is greater than rho u by 2 or not. So, that means that for this scheme to work, what you need to have. So, we have taken as an example delta x E equal to delta x W is equal to delta x. So, your rho and say gamma E is equal to gamma W equal to gamma, let us say this all are the same. So, then your AE will be equal to gamma by delta x minus rho u E by 2. Okay. So, you want it to be greater than 0. Okay. So, that means you want rho u E by 2 less than gamma by delta x. So, rho u E divided by gamma by delta x less than 2, right. Why I have written it in this way is because this represents what? This represents the strength of advection. So, if you multiply say both numerator and denominator by phi, so this is the strength of transport of phi due to fluid flow. So, more the velocity, more will be the transport. So, it is quite intuitive, say you have very strong wind blowing over a surface. So, if there is some heat, faster the wind is blowing, faster it will carry the heat. So, that is this strength of advection, and this one is the strength of diffusion. Okay. So, because this is like k by delta x, so it is like conductance for heat transfer. So, this is advection strength and this is diffusion strength. So, you have this is as a physically it means advection strength by diffusion strength. So, that has to be less than 2, not globally, but based on this length delta x. So, this ratio of advection to diffusion is known as Peclet number. PE. So, for a physical problem, if say L is the length of the length scale, the Peclet number will depend on the length scale L, but this is not the overall length scale of the domain, but only for the cell or control volume. So, this is called a cell Peclet number, that means Peclet number with respect to the dimension of the cell or the control volume. So, you can see that this is like a conditionally stable scheme where your delta x. So, if you see what is its value coming? Its value is coming is rho u e into delta x by gamma. So, this has to be less than 2. So, what is there in your hand? In your hand, see, rho is not there in your hand, because it is the density of the fluid that you cannot change at your will. So, this is fixed. Velocity you have already got from the fluid flow equation, whatever is the solution, that also is not there in your hand. Gamma is like that, say thermal conductivity etc. So, that is a property of the fluid, that also you cannot change. So, the only thing that you can change is delta x, because it depends on your choice of the grid. So, here you see that there is a restriction in this, just like you had a restriction in the time step in the explicit scheme, you have a restriction in the grid spacing in this central difference scheme. So, this scheme works good so long as you obey this restriction. So, one way is to make it so fine that it will always be satisfied, but that also you cannot guarantee, because a problem can you can have varying properties, varying velocity. So, when it will be satisfied and when it will be not satisfied, that you do not know, even though if you make delta x very small. So, this can go out of your hand in terms of giving a physically realistic solution, and that is why the central difference scheme, typically although very appealing, we do not normally use for solving the convection diffusion problems, unless we are absolutely sure that this is going to work for all cases. If you are absolutely sure, it is quite simple, because it is a linear interpolation. So, that is what makes this restricted. So, we should go for something which is very different. Now, if you see, if you understand physically that when there is a chance that this can become large, so maybe density or gamma and delta x, so these you have fixed, but when you are running different problems, different situations, this u can blow up, u can be large, you can have a large velocity, and if you have a large velocity, then it will blow up. So, the large velocity situation or beyond the threshold value, so that this is not satisfied, is your vulnerable situation, and large velocity means actually what is happening, that you have a fluid flow sweeping the entire thing quite fast from the west to the east, that is what is physically happening. So, if such a situation comes, we know that this is not likely to work, because u being large, it may become greater than 2. So, let us try to develop a discretization scheme by keeping that as a possible scenario for deviation from here, and that motivates to the development of this, which is known as upwind scheme. So, in the upwind scheme, so what you see is just see this simple picture. I mean, I will try to make it even simpler by drawing a simpler schematic on the board, and then possibly you will understand it more easily, and then we will refer to the slide for just the algebraic part of it. Conceptual part I am trying to explain here. So, let us say you have this one dimensional scenario, you have the capital P, then you have capital E, and you have capital W, and this is your small w, this is your small e, and you have a say high speed unidirectional flow like this. This is the physical scenario we are just thinking about. So, where was the vulnerability? The vulnerability was interpolating the left hand side by a function which is a linear between the two grid points. So, what are your possible choices? Of course, overall thing is you have to change that interpolation. So, how can you change that? There are two ways. One is you can change that to a more complex variation, or you can change that to a more simple variation. So, usually people who are not familiar with how scientific topics are developed will try to go for complexification, because the general understanding is that more complex the thing is, that should capture more complex scenario also. But the beauty of science and beauty of any advancement in a subject is that all major advancements have taken place where maybe a complex scenario has been represented in a very simple way. Just diverting from here, we have learnt many equations from our school days. Now, very early in say the school level science, when the mathematical forms were there introduced, we have learnt about that E equal to mc square, Einstein's thing. Now, you cannot have any such a complex theory leading to such a simple equation. Usually if the equation is so simple, our intuition is that the concept also is very simple, but that mass energy equivalence is not that simple a thing, it is not intuitive at least, or it was not that intuitive at the time when Einstein was working on it. But the beauty of it was its simplicity. So, one has to understand that if you see pages of equations written, that does not necessarily mean that it is glamorous. You have to see that what is that essence that it is carrying, can you simplify it to an extent. So, this scheme tries to do that. So, what it says that if UE is greater than, so let us concentrate on, let me try to use another color. So, let us concentrate on here. So, you have something as UE. So, your objective is to write an interpolation for UE in terms of P or E or a combination of that. In the finite in the central difference, it was half of whatever was used, it led to this half here plus and half of this plus this. So, now not really U. So, overall rho UE, say rho E UE phi E, because UE already your main interpolation challenge is phi small e. Okay. So, what it says is that if it is a strong unidirectional flow, then you have phi small e equal to phi p if UE greater than 0. So, what it is simply saying that if the fluid is flowing very fast and along this direction, then whatever is the value of phi here, it is mostly due to this. That means the upstream motion is influencing it the most, and it is quite logical, because the downstream will try to influence more and more when you have diffusion also in the opposite direction influencing. But if the Peclet number is significantly large, then the diffusion from the other side is not going to influence that much. So, the value of this is strongly influenced by value of this, and that is the expectation of this scheme. So, instead of linear, it is just like a constant, even the simplest form of linear. And if it is the other way, that means you have fluid flow in this direction, then it is phi E, that means because it is then coming from capital E to small e if UE less than 0. Okay. Now, if you want to combine these two in the form of a single statement, so that is what is written here. There is a function this A comma B with this angle bracket, it returns. So, you can say it as max of A and B, maybe you can define or such functions are there in inbuilt as in many programming languages. So, this will return out of these two whichever is larger, it will return that. Okay. So, look at that. Now, look at the first expression that is written. So, what it does is basically combines these two different steps into a single. So, it says that rho u phi e is equal to phi p into max of rho u e comma 0 minus phi e into max of say minus rho u e and 0. Okay. So, if you take the first example that phi that u e greater than 0, if u e is greater than 0, then max of rho u e and 0 is rho u e, right, and then max of minus rho u and 0 is 0. So, this will return 0 and this will return rho u e. So, effectively phi small e will become phi capital P. On the other hand, if you have u e less than 0, then out of rho u e and 0, 0 will be maximum. So, that this term will be 0, and then out of these two, if u e is negative, this will be greater. So, that will be returned and this minus will make it plus. So, phi small e will be phi capital E. Okay. So, that is nothing but a very neat coding way of combining these two together in the form of one statement. And similarly W, I am not getting into that because it is the same, just your points have changed, grid points have changed. So, then what you are doing is you are now putting this new interpolation, what is there at the top, in the left hand side, and right hand side you are still using the linear. Why? Because right hand side, if you put a constant, the derivative will be 0. So, you cannot capture the dt dx or d phi dx. Now, this is one strength of the finite volume method, that for different physical terms you can use different interpolation or different approximating functions, which is usually not the flexibility for any. Yes, tell.
If rho u is less than 0, then the overall term will become negative, as that is minus phi into max of rho u e comma 0.
No, whether it is negative or positive is different. So, your objective is to reproduce phi small e is equal to phi capital E. Value algebraically whatever it is, you have to look into symbolically, okay, because you really do not, even phi can be positive or negative, that is a different thing. Okay. So, we have to see that whether this particular expression is reproducing this, that is it. Okay. So, now if you are putting the values here, you will see that you have now got a scheme where in the left hand side you have effectively taken it as a constant value at a particular grid or a node, and right hand side a linear variation, piecewise linear variation. So, this is called as an upwind scheme. Now, this is, there can be many variants of the upwind scheme. This is like you have taken just maybe one point, say these 2 points to describe the upwind. Someone may take, for example, say you have this point E. So, the value at E, someone may take that it is influenced by not just P, but maybe also at W, because if that will represent more effect of the upwind grids. But if you take 2 points, it will become a quadratic. So, more points you take, see this is like basic maths of interpolation. So, more number of points you take means you have more unknown coefficients. So, more unknown coefficients can be accommodated only by higher and higher order polynomials. So, more number of points you take to build up a approximating function, maybe your approximation is more accurate, but the cost that you have to pay is that you are working with higher order interpolations, and that also may not always be accurate, because who knows that when you substitute that it may violate one of the basic rules out of the 4 rules. So, the moral of the story is, if we can keep it simple, let us keep simple. So, if we do it like this, now you have the coefficients and you see that you are always using a max function. So, the max function is not returning anything in these two cases, not returning anything which is less than 0. If the thing is becoming negative, the max function is returning 0. So, you do not have any chance of any coefficient becoming negative. Okay. So, it is satisfying the basic rules, but having said that, you have to keep in mind that this is the other extreme of the previous case. The previous case, we like the central difference scheme, it would work for low Peclet number, that means advection strength is much less than the diffusion strength, and this will physically be very good if it is high Peclet number, because it is almost like the high velocity sweeping the entire thing. So, the two schemes are as if keeping in view about physical scenarios of low and high Peclet number, although you can apply it for any case, but they will physically be matching with those situations. In reality, you may not have either very small Peclet number or very large Peclet number. So, then it may not be a bad idea to see that in reality, if you have say a situation where you are just keeping the Peclet number as a parameter, neither large nor small, and try to see that how your solution is there for the limiting cases of very small and large Peclet number. So, to do that, this one dimensional equation, only this one dimensional form can be analytically solved. So, you can solve this analytically, and it is an exponential form. It is quite easy to do it analytically. If you just put the boundary conditions and the solution is given, and how the exponential form comes is because you have this d phi by phi. So, if once you integrate it, it will be ln phi. So, then that phi will be e to the power something, and that is what that exponential form comes. So, this is the exact solution. In fact, someone can use this exact solution as a approximating function. You can say that if it is exact, why then you are calling it as an approximating function? We are calling it as an approximating function because let us say you have even a one dimensional problem. You have the values given these 2 points, but say there are in between 2 points and you are applying this solution. So, these boundary conditions are not known. So, if the boundary conditions are known, then this is the exact solution, but if these are not known, so you cannot call it like exact solution, but overall the trend will be very similar. But if it is 2 dimensional, 3 dimensional, this will not be the exact case, but this is a good motivator to develop an interpolation function. But nobody uses this in practice, knowing fully that this is going to be very accurate. So, in fact, if this is put into that your left hand side phi small e and phi small w, and then it is integrated, then you will get some discretized form, but people will usually not like to do it because you have exponential calculations, and exponential calculation, that is e to the power calculation, in computation is quite expensive, because you have to calculate a large number of terms of the exponential series e to the power x. Okay. So, in that way this is always a golden rule for computation, that we should try to avoid such exponential calculation. And another challenge with exponential calculation is that the e to the power, that argument, if it is large, then exponential can blow up numerically. So, in that way the exponential scheme there is a so called exponential scheme. I am not getting into all the schemes because it will be then like a full 1 semester course. You can again go through my NPTEL lectures, but I am trying to give you the in between line understanding of how these algorithms have been developed. It is very important to know this because see there are two ways in which students learn a subject, and we have also been students. Say there is a geometry, and if say in junior class you are told that construct, take line AB, draw a perpendicular to that at the point D, then draw an angle this, and you are faithfully doing that, and then you are solving a problem, and then also you learn it. But the learning, the challenge of that learning is if you are not thinking by yourself why I should draw that perpendicular, then that remains unanswered. So then you become mechanical, whatever is already there in the book you can learn it and produce it, but when innovation is expected from you, you do not understand the philosophy of innovation, then you cannot do any new thing. So if you are developing a new algorithm, you must appreciate how the previous algorithms were conceptually developed one from the other. That will give you the training of being innovative in developing new algorithms. See, innovation does not come out of magic. These days people say someone is very innovative. So innovation does not come out of magic, it is not common sense. A lot of training where you are trained to think is going to give you innovation. So this is not more of like what scheme is written in the book and that is reproduced with integration and differentiation, that is not the spirit. The spirit is how it trains us to develop from one algorithm to the other. So you can see that if the Peclet number is 0, then it is like the central difference scheme, that linear. That means for low Peclet number it is fine, and if the Peclet number is large, much less than -1 or much greater than 1, in both cases the magnitude is large, you can see that it is very nicely reproducing the upwind scheme like a constant. But if it is in between, then there are ways of say representing this exponential function by some low cost function. Low cost means computationally low cost. So what can be done? You can maybe say there are many ways to do it. So let us say you have an exponential function like this. So you can represent it possibly by maybe one tangent like this, maybe another tangent like this, and maybe a asymptotic constant, because say exponential decay will bring a constant. I am just giving one example. So it may be possible, so forget about this intersected part. So you can combine this by say 3 different linear functions and make sure that they are continuous in value when they join. So this is a representation of a complex function, not complex in a sense that it is really very complex, but complex to compute, to some simpler functions which are easier to compute, but not maybe one such function will do, but you can make a piecewise linearization and then combine it. So such a scheme is there, it is known as hybrid scheme. But sometimes exponential also can be represented by approximately not e to the power form, but a function with a certain power. So that may give an approximation, and Professor Patankar found that with some value of that power it closely reproduces this one, and that scheme he gave a name power law model. So all these are motivated by the fact. So if you see now the summary of understanding. So we started with the finite difference or central difference because that was the intuitive thing that we were carrying from the diffusion problem. We found that it has a problem. Then we went to a physical appeal of, well, the problem was that if the flow is strong then Peclet number would be large and then there is a problem. So we found out a solution if the Peclet number is large and it physically reproduces by the upwind scheme. But in reality when it is in between, it is exponentially represented in a nice way, but exponential calculation is computationally expensive. So there may be more simplified forms of doing it through other forms of interpolation. One is that piecewise linear, which is the hybrid, and representing it by a power law is the power law scheme. Okay. So, this is all about convection diffusion problem. Now, maybe we can get into say 1 or 2 examples, the review questions. So, let us say that you have a condenser in which you have the temperature variation. So, the left hand side is the mass flow rate into specific heat into rate of change of temperature. So, this is like you can say the advection, and the right hand side is the rate of heat exchange, which is U is capital U is the overall heat transfer coefficient into capital A by L into T naught minus T, where T naught is a reference temperature. See, for solving this problem you do not have to really understand what it is physically, but sometimes if you know it, it is good, but at the end it is a mathematical problem. So, what you are asked to do is define a non-dimensional temperature, theta is T minus T in by T naught minus T in, where T in is the inlet temperature in the heat exchanger, and you use a non-dimensional x and call it y equal to x by L, and you take 5 grid points and use the upwind scheme. So, this kind of question sometimes we give in the exam to recognize that, see, there are 2 ways we test that how a student has learnt a subject. One is that you give the scheme algorithm, student can mechanically write the code with those things given, replace P by I, P E by I plus 1, W by I minus 1, and write a code. That is mechanical, that means even if you do not understand what it is, from the formula you write. But the other is, do you get a physical feel of what it is? So, this is such a test. So, I always prefer that this is the test, this kind of thing everyone should do before getting into the computer exercise, at least 1 or 2. So, if you look into this equation, so when we have replaced the temperature with that non-dimensional variable theta, then we have come up with that equation, that means d theta dy is equal to 2 into 1 minus theta. So, that is just algebraic manipulation. So, your objective is discretizing d theta dy is equal to 2 into 1 minus theta by the upwind scheme. So, if you now, so first is finite volume, means you have to integrate it with respect to your control volume. So, your variable is y. So, you integrate it with respect to y. So, you now have d theta dy. So, you have theta small e minus theta small w, that is d theta integrated from small w to small e, and in the right hand side it is just like a source term. So, you may take this theta say equal to a constant which is theta p, and then you can take that out of the integral. So, integral of dy will be delta y. So, now you have your equation where you have a discretized equation. You can write it as this AP into theta p equal to AE into theta e plus AW theta w plus B. There is a B because there is a source term. Here it is a sink basically, maybe heat is lost. So, with all the values given, so you have 3 equations, and these 3 algebraic equations, in fact 4 equations, because you have 4 grid points, you can solve them and you can get the values, very easy to solve them, even by hand calculation, and exact solution you can also find out, analytical solution, d theta dy plus 2 theta equal to 2. So, you can get the analytical solution, and with these values if you make a graph of the numerical and analytical, it will give you a complete picture of what your scheme is doing. Okay. And you may vary the parameters and see for which parameter your scheme is doing well and for which parameter your scheme is not doing well. So, these kinds of things, this may look to be very simple, but this is really the understanding of the subject. So, we close this particular chapter, and maybe we take a short break of about 5 minutes, and we will then get into the next chapter, which is the next session, which is the fluid flow problem, that means numerical solution of the Navier-Stokes equation. the next one, our topic, which is perhaps the central thing that we look for in any CFD exercise that we are going to do, that is how we solve the fluid flow equations. So, we have solved diffusion type of problems, and many times fluid flow is also a diffusion type of problem. For example, if you have negligible acceleration or inertia is not present, it is like a diffusion problem. Many times you are solving a convection diffusion problem where the flow velocity is known. So, that is also not like a real fluid flow problem because flow velocity is known, but the issue comes for this particular topic is where the fluid velocity is not known, and that is what we are going to do or we are going to see. Now, just like any other problem that we have discussed, so we will look into the equations first, that what are our equations. So, we have to remember that fluid flow is not just force balance, it is also mass balance. So, mass conservation, that is the continuity equation, and the force balance or the Newton's second law expressed in terms of the Eulerian variables, that is the so called momentum equation. So, you have the momentum equation. So, let us say you are using a Cartesian coordinate system x1, x2, x3. So, you have the momentum equations in the 3 directions. So, what we are going to see is that how those momentum equations will look like. It is not necessary to expand the momentum equations for solving all our problems, because we can write that in a compact flux form, but sometimes it is not a bad idea to expand, because you will then get a full feel of what are there in the equations. So, you have I equal to 1, I equal to 2, similarly I equal to 3. So, now if you look into these equations, so you have 4 such equations, one is the continuity and the 3 momentum. Before attempting the solution, we have to understand that what is that special feature of this that we have to take into account, which perhaps we did not have to care for when we were talking about the diffusion and convection diffusion problems. What is the uniqueness of these systems of equations? Now, usually when you have a set of equations, and this again from our very school level training, we always try to match is number of equations and number of unknowns. If you have multiple equations and you are formulating those equations, at least we see that do we have enough equations, not just any equation but independent equation, not somehow equations are constructed. So, do you have that? So, it is an accounting that we are all trying to do, number of equations, number of unknowns. So, how many equations we have? We have 4 equations, right, the continuity and the 3 momentum equations. So, you have 4 equations. What are your unknowns? When we say unknowns, we have to write it very generally. In some cases that unknown may be known, but generally what are unknown? So, in all cases you have this velocity u1, u2, u3, or in a different name u, v, w, whatever it is, these are unknown. There is a pressure that is unknown, and density also may be unknown in general, right. It may be known for some problem, but in general it may also be unknown, right. So, you have 1, 2, 3, 4, 5, you have 4 equations and 5 unknowns, right. So, this is not our accounting. That means with this accounting we are getting something less in terms of our equation. So, we need more equations. So, one of the equations, if density is say not constant, it can vary with what? It can vary with other properties, and if you have a simple compressible pure substance, not changing its phase, then density can be written as function of two other independent intensive thermodynamic properties. This is from basic thermodynamics. So, for example, you can write density as a function of pressure and temperature. The simplest way in which all of us have learnt how to write it is ideal gas, P equal to rho RT, right. So, that is this one as a specific example. For other fluids, it is not this P equal to rho RT, but you can use the van der Waals, so many other equations of state are there. So, this is the mathematical form of what is called as equation of state. Okay. Now, see, with every new thing you are bringing in another trouble. So, what is the trouble that you are bringing in? Now you have temperature. So, one way where you have no more trouble, trouble means what? Needing to solve additional equations, that is computationally trouble, is if T is constant. So, that is an isothermal problem. But if the problem is not isothermal, then you need a governing equation for temperature, and that is your energy equation that we talked about. So, that is how you see the fluid flow and heat transfer are connected when you have this convection. So, in that way, if you have this and the energy equation, that completes this thing, but then you have the description, but that is not all, you have to solve it. So, to solve it you recognize certain things. Number one, these are coupled partial differential equations, because the solution of one is influencing the other. These are non-linear partial differential equations, where the non-linearity comes, the left hand side, see that term partial derivative with respect to x1 of say rho u1 into u1, one such. So, that is a non-linear term. So, in fact, all those three terms in the left hand side after the unsteady term, they are all non-linear terms. So, dealing with non-linear equations is a challenge, because linear equations you can use certain properties both for analytical and numerical solution, but non-linearity handling usually will require always iterative method, and that iterative method it will have its sort of vulnerability to convergence. You cannot use something like the Lax equivalence theorem, and you have to do the grid independent study, all those things come up. So, non-linearity, coupled nature. There is another aspect. So, you have in the right hand side a variable, a dependent variable pressure, but you do not have any separate governing equation that is explicitly talking about pressure. So, this is a big problem, handling pressure, that you have pressure in the right hand side in all those three momentum equations, but you do not have a separate governing equation for pressure. Continuity equation is not a separate governing equation for pressure. So, how to go about it? So, your solution of this Navier-Stokes equation is about developing a management to overcome these issues, and that is why it makes a bit more involved as compared to whatever are the foundations that we have learned for the diffusion and the convection diffusion problem. Now, as the numerical thing developed, see, any subject develops with lot of the subject's insight, but not by keeping common sense away. Common sense is the most important thing for learning anything. So, when you see that pressure is creating a trouble, so one way is that you eliminate pressure. So, how you can do it? See, I will just write this in a vector form, this Navier-Stokes equation. So, you have So, what I have done is I have just written it in a vector form, okay, very compact. My objective is not all on all the terms, but focus on the pressure term. So, how do you get this vector form is very easy. If you have the 3 components, multiply the x component with the unit vector along x, y component with unit vector along y, and z component with unit vector along z, and just add, you will get the vector form. So, focus on this term. So, if you want to eliminate it, you can use a simple vector calculus identity that you have curl of gradient of a scalar function is a null vector. This is a vector identity. So, what you do is you take the curl of both sides. If you take the curl of both sides, then the curl of this curl of gradient of pressure, it becomes a null vector, right. So, you have eliminated pressure, and that means you are now dealing with curl of velocity. So, this becomes an equation where your variable has shifted from velocity to curl of velocity, which is called as vorticity. So, that is the resulting equation is known as vorticity transport equation. And vorticity typically you cannot just deal with vorticity in an isolated manner. Typically vorticity is connected with stream function in a 2-dimensional incompressible flow. So, that is called as stream function vorticity formulation. We will not get into that. I mean, it is always good to learn that, but it has its restricted appeal, because see, for every problem you have to give boundary condition, but vorticity is not your fundamental physical variable, or stream function is not your fundamental physical variable. Your fundamental physical variables are velocity and pressure. So, to give a boundary condition in a physical problem, it is quite intuitive that if you have the physical description of the problem in terms of velocity, pressure, you can write something which is the physical problem. So, these are called as primary variables or primitive variables. The stream function and vorticity are mathematical variables. So, they are derived variables and they are not primitive variables. So, making boundary conditions for them itself can be a problem from a physical system. So, usually we like it to use the primitive variable, but that vorticity, at least what it is doing is it is giving the advantage of eliminating the pressure, but it brings in the trouble of introducing 2 artificial mathematical functions, vorticity and stream function, not really artificial but derived. So, you have to then give a boundary condition on those which is not naturally defined for a physical system. So, this is not a very good approach of solving all types of problem. Maybe for some type of problem you can very easily describe vorticity and stream function for different boundaries, but it is not quite trivial to do for all. So, this approach is very limited, but this is the intuitive approach. Now, intuitive approach is something, sometimes it is funny, like say you have headache. So, if you cut your head, then you will not have headache, right. So, that is the intuitive approach. So, you have pressure is your headache, so you get rid of the pressure term, then there is no problem, right. So, that is we are having this physiology, modeling of physiology. So, the remedy is if you have headache, you cut your head. So, this is modeling and simulation of physiological flow, right. So, now that you cannot do it like that, and so when we have headache, we try to make a remedy by keeping the head. So, we will now see the remedy by keeping the pressure gradient term and see how still we can manage it. So, we have to recognize that the major aspect that we have to deal with is that you do not have a separate governing equation for pressure. So, artificially you have to construct a separate governing equation for pressure, and what you have in your hand is the continuity equation, which is not a governing equation for pressure. So, The trick is develop an algorithm where you convert the continuity equation in a discrete form to make it a governing equation for pressure, and that is the whole ball game that these all fluid flow solvers they are trying to do. So, here what I have done is I have tried to summarize the challenges in or what are the issues in the Navier-Stokes equation. What I have talked about is a summary of this. We may not have as many equations as number of unknowns, the momentum equation is non-linear, the continuity and momentum equations are coupled, and pressure field is unknown, but there is no explicit governing equation for pressure. And you are having also other challenges which I am not explicitly telling, that you have a say turbulent flow. Now, if you have a turbulent flow, what you have at least got a feel that to solve a physical problem you need a time discretization and space discretization. So, for a turbulent flow you have wide range of time scales and wide range of length scales. So, the resolution has to be really fine, where you are trying to capture the physics from all the way to the large eddy, which is like of the channel size, to the smallest one which is like the molecular dimension. So, it is not straightforward to do, although in principle you may apply the Navier-Stokes equation, but it will go to such a huge computation, then only for a selected class of problems with very high performance computing power available you can do it, that is known as DNS, direct numerical simulation of turbulent flow. So, that is a challenge, but that is numerical and analytical solution for that it is still not there, and that is why out of all the you can say unsolved problems in classical physics, turbulence remains as an unsolved problem. There are statistical ways of dealing with it, but fundamentally it remains as an unsolved problem in physics. So, in that way, so that is one. There is another aspect which we will not cover as a part of this course, but very important, that sensitivity of your solution to your input values, maybe boundary condition as an example. So, you are having an experimental measurement. So, you are saying that at the entry of the pipe the fluid is entering with uniform velocity, with velocity as 1 meter per second. So, you are solving a CFD problem like this. Now, where from you get this? Maybe you have got some experimental data from which you have averaged, that is the best thing that you can do, but your experiment will have uncertainty. So, you will have lot of uncertainty in even prescribing your input, and that uncertainty can get into spoiling your output. If not spoiling, it can give a range of possible errors. So, when we are doing experiments, normally if you have experimental data we draw an error bar, that is an upper limit and lower limit. CFD people normally would not give error bar, but it is not correct, because whatever solution you are giving, you should also give a feel of what could be the maximum upper and lower bounds. Say you are predicting the value of pressure of blood of a human patient and giving it to a doctor. Now, you have lots of uncertainties, uncertainty in terms of many things. Patients, the boundary conditions may not be well described from some medical investigation you are approximating, the properties of tissues or blood may not be well properly described. So, all these are uncertainties. So, it will compound to an inaccuracy in the solution. So, if you give the doctor not just the solution, but upper and lower bound, then the doctor will have confidence, okay, if it is not the real value, the exact value, at least it will be bounded by this. So, that itself is a different subject altogether, and nowadays it has become very important and advanced because of the advancement of data science. So, how data science has enriched and contributed to recent advancements of CFD, towards the end of this course I will give a particular session on that. So, at least what we can recognize is that uncertainty quantification is a very important thing, and there are different ways of doing that. One very popular method is known as polynomial chaos, is a way, a mathematical technique of it is like a sort of a spectral method type. So, where you are trying to understand the uncertainty of your numerical solution. So, all those things are there, that means that it is not at all straightforward that you give a value and you get a solution and you accept it. So, now pressure is one of the things, it is not just giving a challenge in terms of having no equation for pressure and you are trying to sort of manufacture one equation for pressure, but also how to discretize the pressure gradient. So, we are trying to see that what happens, what is the challenge if you want to discretize the pressure gradient. So, pressure gradient is a very simple term like dP dx. So, if you integrate it say from small e to small w, it becomes p small w minus p small e. So, you have, let us say you have small w higher pressure and p and small e lower pressure and fluid is flowing from left to right. So, this is a very important parameter which is the driving force for the fluid flow. Now, again the question comes interpolation. So, interpolation, so how do you do that? So, if you take that central difference scheme, so p at small e is then half of p at capital E and plus capital P, and this motivation for the interpolation is clear that our variables have their values to be solved at the capital or the uppercase grid points. So, you have to transfer the lowercase ones to the uppercase ones. Similarly, p small w. So, if you now find the difference p small w minus p small e, you get this as half of p capital W minus p capital E. So, nice expression. So, can you tell what is the problem with this? Because expression is very nice, but this is not acceptable. So, when you want to find out a problem, always try to understand the most extreme case. Let us say you have Pw equal to Pe, then that means P capital W equal to P capital E, then your right hand side is 0. So, we are having 3 points which is our focus, capital W, capital P and capital E. Let us say we are plotting pressure versus x. So, let us say we have a situation like this. So, you have P of capital E equal to P of capital W. So, this is one case, but you can also have something like this. Now, this is actually non-zero pressure gradient and this is also non-zero pressure gradient, but this is not able to capture that. So, it can predict something which is physically unrealistic, because somewhere the value of pressure at the point P is nowhere coming into your picture, right. So, you need a remedy for this. So, how do you do? Now, how do you get a remedy for this? Now, you have also similar points similar for velocity, because you have this velocity integration also very similar, like pressure gradient, velocity gradient also the same. So, nowhere the value at capital P is influencing your solution. So, as if whatever is the value of capital P, your answer would be same, but it cannot be like that. Your answer should be influenced by the value at capital P, right. So, one of the ways, this is just one of the way in which this remedy was suggested, is you go for something which is called a staggered grid. That means you use different grids for pressure and velocity. So, if you look into this diagram, so you have this, so whatever control volume is constructed there. So, you have, I will show in the next slide, that you have two different control volumes which are considered for the velocity and the pressure calculations, and they are little bit shifted from one another, and that is why the name staggered grid. But just to make you familiar with the nomenclature, if you can still manage to work with the same grid point for pressure and velocity, then that is called as collocated grid. See, the staggered grid had a problem when? The staggered grid had a problem when we are trying to do linear interpolation, but if we are using higher order interpolation functions, then actually it is not necessary, because then it can accommodate the effect of P. So, collocated grid formulation also is quite common, and when these subjects developed, they all developed with the say geometry of these rectangular type of grids. But with the advancement of geometric modeling, now the method can take any different shapes like triangular or any other forms of the control volumes, and they need not be so well structured in a stencil like I comma j. So, that is called as an unstructured grid or unstructured mesh. So, if an unstructured grid, this staggering has no meaning, right. So, then it is better to have calculation at the same point, and that is why collocated grid is used for that. But the staggering is a very important concept, because conceptually it tells that how to overcome this unrealistic thing that comes in the interpolation. So, remember that what we are doing, the staggered grid is one way of just illustrating it, but the overall conceptual foundation of how to derive the equations, that does not depend on whether it is staggered or collocated grid. So, in the staggered grid, the benefit is that you do not have to interpolate the interfacial properties, that was the problem, and so this kind of wavy field you will not get unrealistic, and pressure is going to drive the flow, but staggered grid will mean more bookkeeping. That means you need to have a separate accounting for the pressure grid points and separate accounting for the velocity grid points. So, how do you stagger this? Maybe let us go to the next one. So, if you consider now these diagrams, it will tell you how do you stagger this. So, what you do is you take your momentum equation or velocity in a way that the capital letters are not, or the uppercase ones are not your grid points, the lowercase one are your grid points. So, it is shifted. What you see in the diagram, say in the x direction, for the discretization that we were talking about in the diffusion or the convection diffusion problem, P would be at the center. Now, here small e is at the center and capital P and capital E are at the boundaries. So, why? Because then if you integrate the dp dx, it will be P at capital E minus P at capital P, and you do not have to interpolate it. So, in that way, if you see, you will get in the x direction, y direction and z direction, it is staggered or shifted, and this staggered means it is staggered with respect to velocity calculation. Okay. So, with respect to velocity calculation in the momentum equation, these are staggered. So, your grid points are now the small letters and neighbors are also small letters, and that is how different names are a bit change in the name has to be given, like you need a grid point which is in the right neighbor, but you have already exhausted the nomenclature small e. So, 2 small e's e like that. Okay. And if you are writing a code, you have to keep in mind that your indices, those I and j, for main and staggered you have to be very careful. Okay. So, once you have this, now even if you did not have the staggered grid, you will get the equation in the same form for the collocated grid, only instead of small letters it will be the main capital letters, that is it. So, now what we will see that how to solve these equations. So, the 3 momentum equations for u, v and w are this, as I told that because these are non-linear you require to go for an iterative scheme. So, you start with an initial guess. So, you make an initial guess for pressure P star. So, why? So, if you make an initial guess for pressure, then your equation becomes like any other equation, because pressure was the extra thing which was creating headache. Now, you have assumed something. So, it has become like a pseudo constant. But if you are putting that in your equation, definitely your equation will not be satisfied. So, if you are putting P star and in turn you get the solution U star, V star and W star, these are not the correct answers of U, V, W, because pressure is a guess. So, the resulting velocity is also not correct. Until or unless you are a magician, you have given the correct guess for pressure and it is giving the correct guess for velocity. So, all what it means is that after you solve these 3 equations with that guess pressure, you have 4 different variables which are your not correct variables, P star, U star, V star, W star. So, how they will become the correct P, U, V, W? If you add the correction which you do not know. So, you have your actual P is equal to P star plus the pressure correction P dash. So, you have the concept of pressure correction and velocity correction. So, in an iterative scheme you are having pressure correction and velocity correction to make sure that from your inaccurate value it is going to converge after some iterations to the correct value. So, now the challenge is that how do you estimate these corrections? You do not know. So, to estimate these corrections, see, even if you do not know anything, say you are solving some equations. So, we have exhausted the use of momentum equation, 3 momentum equations we have used, continuity equation is still in our pocket. So, we have to see that how we can make use of the continuity equation to make an estimation of these corrections, and the entire way in which the algorithm is developed with that objective it is translating into a mathematical form. So, look at this equation. At the top you have, so had your values been correct, the left hand side would be U and right hand side would be P. When it is not correct, left hand side U star and right hand side P star and also U star. So, now you subtract. If you subtract, you just use the definition that U minus U star is U dash and P minus P star is P dash. Now, to that extent you have the first term and the last term quite well described, but this neighboring term is something which is much more complicated. So, what this algorithm tries to do is to make the calculation simplified, it drops the neighboring term. So, then you can argue that suddenly it is dropping, so it is wrong. So, what you have to recognize is that it is just a way of getting into convergence. So, if you did not drop it, it might lead to a maybe technically more correct way of getting into convergence, but once it is converged by some way or the other, the correction has no meaning because it has converged to the correct value. So, correction is 0. So, whether you drop it or not will matter in terms of how you reach convergence, but once you have reached convergence that is not going to matter, because our solution is once we have reached convergence. So, omitting that is not going to make us any fundamental error in the final solution. So, if we are omitting that, then you have this AE into UE dash is this. So, you can simplify UE dash is equal to capital AE by small ae, which you give a new name d small e into pp dash minus pe dash. So, you substitute that here. So, you have ue equal to ue star, now you are substituting in terms of this one. So, now you have expressions for velocity in terms of pressure, and then if you substitute pressure correction rather, and if you substitute this in the discretized form of the continuity equation, then you will get a discretized equation on the pressure correction, and that is known as pressure correction equation. So, let us then make use of the continuity equation. So, continuity equation we discretize, and remember that we are discretizing it on the basis of the usual grid, not the staggered grid. Why? Because we are interested to get the values of pressure at the usual grid points. So, we should not stagger this one. So, now if you integrate it, you will get very simple integration, like say d dx of rho u into dx, that is d of rho u, that will be rho u e minus rho u w. So, what then we are doing is we are substituting this u, v, w etc. as u star plus something into the difference in pressure correction. So, if you do that, you will get a governing equation for pressure correction, just like any other equation where you have AP into PP dash is the summation of the A of the neighbors into the P dash of the neighbors plus B, same form of linear algebraic equation that we did for maybe even a 2-dimensional heat conduction problem. So, this is a 3-dimensional, so you have east, west, north, south, top and bottom, very general one. So, this is what is the so called pressure correction equation. So, this equation can be solved, and then you can get P star, and then you can starting from P star you can correct P as P equal to P star plus P dash. So, that will become your new P star, not that with one iteration you have converged. So, in that way you keep on updating your P star, you have the guess P star and then you correct it with such iterative scheme, and once you converge you see that your previous P star and after the iteration new P star is almost the same, and then you say it has converged. So, this method is this is the most popular, and this has been one of the most, I would say, impactful contributions of Professor Patankar, and this is known as simple algorithm. I mean it is a very nice name that he gave. Some students find that it is not that simple, but it is an acronym. It is semi implicit method for pressure linked equations. So, pressure linked equation means pressure is linking the velocity. Why semi implicit? It has nothing to do with that time integration implicit and explicit. So, I will tell why it is semi implicit. So, if you go back to the previous slide, maybe yes. So, if you see in the right hand side, that neighboring term is made 0. So, the velocity correction at a point is related to the pressure correction at the neighboring points, but not with the velocity correction of the neighboring points, but it is actually also a function of the velocity correction of the neighboring points. So, that because of this is called a semi implicit. So, it is not really, it is in a way sort of implicitly connecting pressure and velocity, but not fully, because this is just omitted. So, that is why the name semi implicit method for pressure linked equations. So, what is the algorithm? So, you guess the pressure, solve the momentum equation, that means discretize momentum equation to get u star, v star, w star, solve the P dash equation which is from the continuity equation, you correct P, and then also you can calculate the velocity corrections and you correct the velocity field. So, you take the corrected pressure P as the new guess pressure P star. So, your new P star, and then you repeat it till you get convergence. Okay. So, the Ansys that you are going to use for your calculations, it uses some variant of this simple algorithm, because over a period of time different variants of this algorithm have come, like simplex, simpler, so many other variants are there, but this is the foundation. So, if you understand this, you will recognize that how the velocity and pressure are coupled in a set of equations where you do not have a separate governing equation for pressure, and you are somehow manufacturing it by using the continuity equation. That is the essential learning that you get. So, I have put a few review questions So, let us say you have a one dimensional problem, the momentum equations are like this. So, as if someone has discretized for you and this is your momentum equation. So, you can see that u at the point B is a function of the difference in pressure between 1 and 2, just like your capital P and capital E, and u at the point C, and the boundary condition that u at A is 15. Obtain the values of P1 and P2 following the simple calculation procedure. So, I will just show you how it is done. Again, the whole idea is to get a feel of the method. So, what you now have to do is you have to make a control volume for, see, this control volume is for constructing the pressure correction equation, because your discretized momentum equation is already given to you, possibly using the staggered grid formulation. So, you do not have to do it again, this is given as a part of your problem, but pressure correction is the only thing that you have to formulate. So, we are integrating the continuity, one dimensional continuity is du dx equal to 0, rho is constant. So, continuity equation is u small e equal to u small w. So, in that way, for the grid point 1, if you get back to the diagram in the previous slide, so that means u a equal to u b, right, because its neighbors are a and b. So, the first set of equation for grid point 1, you have the continuity u a equal to u b. Now, you substitute your momentum equation there, so in terms of pressure correction. So, you have u a equal to 5 into 2.5 into P1 dash minus P2 dash. So, and your boundary condition is given, what is the value of u a, you substitute that. So, you will get a equation for P1 dash minus P2 dash. For the grid point 2, you have u b equal to u c, you substitute that, and see, you have u a equal to u b equal to u c, this is physical, that means you have a one dimensional problem, steady state, all points are having the same velocity. So, that is what even the numerical thing is talking about that. So, if you substitute that, you have this star, say I have just marked these two equations as star and double star. So, both of these are giving 15 equal to 5 plus 2.5 into P1 dash minus P2 dash. So, this is where, if this is given in the exam, I have given quite a few times, the CFD course I have taught for many times during my early career, and this problem I used to give sometimes with some change in value, etc. So, this is where most students get stuck. So, I want to solve P1 dash and P2 dash, but I have effectively only one equation, right. So, now you have to keep in mind, and this is a very important concept, that pressure is relative in nature and not absolute. See, even like from your basic idea of fluid statics, we say that pressure at a point is h rho g, school level thing, say you have water and a depth h. So, what does it mean? It means that if you are taking your reference atmospheric level as 0, then with respect to that, if you go to the h level, it is h rho g. So, pressure absolute value is not important for you, and the reason is that in the momentum equation you have dp dx, not p. So, that is delta p by delta x. So, your delta p matters, and you can have many values of delta p for which, or rather many values of p for which you have same delta p. So, say you may have P1 some value, P2 some other value, but still P1 minus P2 all the same. So, there is not a unique solution. So, the trick is that one of these you have to choose as a reference and calculate everything else with respect to that by recognizing the relative nature of pressure. So, let P1 prime equal to 0. So, if you take P1 prime equal to 0, you will get P2 prime equal to minus 4, and then you correct the pressure, and then you can correct the velocity. Here in one step the solution is converged, but this is not magic. There is a reason why in one step it is converged. You think about it and this is like a special very simplified problem, but it is guaranteed whatever you take as your guess in one step it will converge. Sometimes people talk about magic maths, right, they say guess a number, multiply by 10, then they do this and then tell what is there in your mind, then the person will tell this. It is simply an identity that the person is calculating in mind and the final answer will be the same. So it looks, any magic is not a magic. So this is also not a magic, you take any guess, your solution will be the same in one step. Think about it and maybe we will discuss at some point of time. Let us take another problem. So in a one dimensional problem, now you have this one. So just we have added one more grid point and given the boundary condition as one as velocity and another as pressure. So this is just to give you an idea of how to treat a pressure boundary condition. So what you have to do is to write the continuity equation and starting with guess values of P1 and P2, that is P1 star and P2 star, use the simple algorithm to get the result. So I will of course ask you to do it by yourself, but I am just giving you an outline. So you, as I told that you can just take an assumption of the pressure correction. So you assume P1 dash and P2 dash equal to 0 and then from that you can get the U star values and see the continuity equation, and again this is like U small w equal to U small e. One dimensional steady state continuity will be like that only. So you now substitute in place of U small e and U small w the expressions in terms of U star and P dash, and then you get your pressure correction equation. So that will give the final P1 dash equal to P2 dash plus 4. So this is what you get for the point 1. Similarly for the point 2 you will get 4 P2 dash plus P1 dash equal to 30. So if you now solve these two, you will get P1 dash and P2 dash and you can correct that P1 and P2. So again it appears that with one iteration it has converged. So now can you say that in the previous one we were finding that you had one equation with two unknowns, but here you have the equation and unknowns the same. So the only difference is that here you have given a pressure boundary condition. So your relative nature of pressure is set up by the value of that boundary condition. In the previous it was a velocity boundary condition, so you had to set it up with your reference. So that is the only difference, but otherwise the calculation scheme is the same. Now this is a two dimensional problem. So in the two dimensional problem you are given UW, VS, PN, PE etc. Like staggered grid means you are dealing with small letters for velocity and capital letters for pressure. So you are putting that and the control volume in this diagram, of course delta x and delta y are shown schematically different, but for your calculation you can take these as same. Use the simple algorithm to obtain this whatever are not given, that is U small e, V small n and P at capital P. Other points the values are given. So these are actually artificial problems, but these are given to create a concept in you. So you can take, so wherever this pressure correction is not given you can assume something. So what you can do is you can assume the value of pressure. So once you assume the value of pressure you will get a value of velocity, because your equation is of the form U star is a function of P star. So put a value of P star and you will get a value U star. If P star is not correct, U star is also not correct. That is the central philosophy, very simple. From my learning of not just this subject but many subjects, what I would always urge you to do, that try to think simple. make your mind simple. If your mind for learning a scientific subject is like a child, you will learn the best. So, do not over complicate a thing which is actually not complicated. So, once you now you have the continuity equation, you integrate it over the main control volume, and in that you put all those expressions, and once you put all those expressions you will see there is only one unknown, which is the pressure correction at P. So, that is solved, and then you will get the expressions for the new velocity and new pressure, and here also by some way maybe in one iteration it has converged. So, this gives you the overall idea that what we are doing, we are guessing pressure, we are putting that guessed pressure into the discretized momentum equation to get a velocity. Because your guess is not in general correct, that is also not in general correct. So, that velocity you substitute, or once you have that velocity, then you can substitute that velocity in the discretized continuity equation, and because your pressure is not correct, you write that pressure as P star plus P dash, where that P dash you can get from the discretized momentum equation. So, all the velocities are expressed in terms of the P dash, and that expression is substituted in the discretized continuity equation, and that will give you a pressure correction equation which you are solving. That is the whole idea for this. So, with this we end up here for the this fluid flow equation. We will continue with the next topics, and next what we have is I think introduction to this how to work with Ansys, and we will move forward with that.
All right. So, basically your theoretical class is almost done. Now, we want to apply the knowledge you got, we want to apply how to model using any like software. Yesterday you learned how to write a code using MATLAB, okay. And today I want to show you now just theoretically, okay, what the Ansys Fluent has, and in the afternoon we will show one problem, okay. Our one of our tutors will show you step by step how to set up a model, okay. But before I start, I want to make sure that I am not from Ansys, okay. I am not promoting them, but because this software and this methodology, the finite volume technique, this software is actually any result produced from here, validated results, is now is accepted in the research community. Also, when you publish paper, they do not ask any question. So, there are lot of softwares now available, and we have the console multiphysics software nowadays lot of people are using, especially I found in India it is very popular, okay. And that is they use the finite element method. We did not discuss about that here, and that software is called a multiphysics. So, that is not only fluid mechanics, but also some other things like almost all physical problem you can use that software. But this the Ansys also they have a couple of things. They can also model the solid mechanics as well, okay. And Ansys actually, when I did my PhD in 2005 to 2009, I use Fluent, okay, and the Fluent version was 6.3 or something, and this version it was only just Fluent, not Ansys. And then that you need a mesh file to solve in that using that software, and you have to create geometry from some other places, like we use Gambit. Gambit is another software, and we actually created the geometry, we created the mesh, and then we import the mesh into the Fluent. And after that is, I think it is 2010 or 2011, the Ansys company they actually took it from the Fluent. And then also Ansys they have their own another software, it is called the CFX, okay. So, once you have the Ansys, you can see the CFX and the Fluent. Actually, they both can do the same job. I do not know why they capture it, because maybe the to overcome the competition, okay, CFX and the Fluent. So, they bought all together to do the monopoly business, maybe, I do not know. But you can actually try both of them if you want. But some problems like dealing with the particles and those things, I think CFX is better than Fluent. But the problem we actually the theoretical things we already discussed here, Fluent I think is the best, okay. So, some of my slides is very much obvious, we already have discussed. So, I will skip. Okay, so, you know what is fluid mechanics or fluid dynamics. So, but here we want to see that in the brief, the fluid flow can be solved or described by three basic physical law, okay. It has more if we include some other things like the particles or other things, but this mainly the fluid flow, okay. So, that is the continuity equation where the mass is conserved, we already have discussed this morning, and the momentum equation is known as the Navier-Stokes equation. So, that is based on the Newton's second law of motion, and the third one is the energy equation if you want to solve any temperature or some energy field. So, mostly these three equations we will be dealing with using the Ansys. So, as in the morning you just learned that it is the Navier-Stokes equation is highly nonlinear differential equations, and it is not possible to get the exact solution, it is not possible at all. However, there is a millennium question, okay. if you can solve this question, you will get $1 million US is already the declared. So, you can see in the online somewhere. So, people are actually trying to get the exact solution, especially from India. I found one professor, she is very close to the exact solution. So, they are actually trying to solve the analytic solution. So, but still only the option is the numerical solution. Okay. So, now there are 3 ways of solving problems. Yesterday Professor Chakraborty explained. So, one is called the analytical or the theoretical approach, another one is the experimental approach, and the last one is the numerical approach. So, before this computer was invented, there was no choice to do the numerical using a computer, but that time people used like analytical or some theoretical approach. Even in my masters, we actually did some analytical approach, and also in my PhD, half of my PhD is analytical mathematical analysis. It's called the scaling analysis. Okay. The scaling analysis is a very nice way of solving a problem, and the result is very like correct to the same order of magnitude. It is not accurate because you have to exclude some term. For example, we mentioned that we have unsteady term, we have advection term, we have pressure gradient term, we have the viscous term. Okay. So, during the flow development, unsteady flow development, in some stages some terms are important and some terms are not important. For example, very initially when T is very small, then the advection term is not important because the flow does not start. Mostly it is conduction is the important. So, that time we can ignore the advection term, and then we can use the unsteady term balance with the diffusion term. So, this is the way we can actually get some solutions of velocity, some steady state time or this kind of things. So, we mathematically is a very like a algebraic equation we got at the end, but it is very quick, and the result is very accurate to the 1 order of magnitude. And after that we actually validated our result using after solving the full set of equations. Okay. So, the second part is called the experimental approach. So, experimental approach is very nice if you can do that, but sometimes it is very expensive. Especially one of my PhD student, he is working on the electrolysis. Okay. He is breaking water and getting hydrogen. So, producing the hydrogen. So, he is using the PEM technique in COMSOL, but the problem is he needs to do some experiment, but we cannot set up it. It is a huge expense, we cannot do that. So, we are actually trying to get some data available in the research community, and then we want to validate our model. So, that is why it is not always possible to do the experimental approach, and sometimes it is not possible to do the experiment. Okay. You cannot do the experiment if you want to do the lung research, you cannot take your lung out and do the experiment. Okay. So, we have to do some other way. So, the numerical approach, as you have seen that it is cheap in that sense that it only needs the computer, okay, and your knowledge of how to solve it. And this now is computer is not very expensive, is a bit cheaper. So, we can solve the problems, although this is not very accurate, this is approximate solution, but it actually help a lot. Okay. So, if someone wants to build up something like the aircraft or something, so aircraft they actually started in 1960. Okay. They are actually using this on very badly the CFD, because that help a lot. They have some idea, okay, how to design the machinery, how to do it. So, they need some idea what will be the Mach number, maximum Mach number, and those kind of things. Though that is why they want to use this CFD, and it is very quick. Okay. So, what is CFD? So, you already know that the computation fluid dynamics is a set of numerical methods, okay, So, these numerical methods, a lot of methods that actually give us the approximate solution of the problems of like a fluid dynamics or the heat transfer. Okay. So, the CFD is not a science itself, it is a tool, okay, that actually help in different discipline to get the fluid flow or heat transfer, this kind of results. So, the CFD solution are not exact, then why not use the analytical approach? Okay. But as I said, it is not always possible to get the analytical or the exact solution, and experimental approach is more reliable, such as wind tunnel experiments, then why not use experimental approach? So, the answer is the CFD used because there are many engineering problems that can't be solved by analytical or experimental approach, and it is difficult to use analytical experimental approach. I already mentioned it. So, difficulties like a theoretical approach and the experimental approach. So, more here. So, the approach gives exact solution which is great advantage, but analytic solutions are only possible for limited number of problems or very simplified problems that I already mentioned, the scaling analysis. So, we have to ignore some terms, although we are ignoring, but it has some influence. Very initial time it already trigger, okay, the buoyancy. So, we should not completely ignore it, but we do it because of the to apply the theoretical approach. And experimental, as I said, the major challenge is the expense, and the other is the it has lot of uncertainties to actually do the experiment, because when you set up a numerical model, there is nothing that environment is influencing it. But if you want to do like some experimental setup, there are a lot of things affecting. For example, if you want to do some heat transfer, so your room should be exactly the same temperature, okay, if it is like isothermal cases, but it is realistically it is not possible, because always some heat transfer is happening. So, we cannot actually set up very nice as like a numerical approach. A numerical approach we can ideally give all the correct value. Now, CFD has some application, a lot of application. I think you can do everything in CFD, and especially for the aerodynamics of aircraft and vehicles, where we calculate the drag force and the lift force, and the power plant, the combustion of internal combustion engines and gas turbines, and the hydrodynamics of ships, and biomedical engineering. We will discuss about the blood flow through arteries or veins, and some environmental engineering is just distribution of pollutants, that I will give my, when I give my lung problem, I will discuss about this one, the pollutants. So, in a nutshell, CFD applied is almost every discipline of engineering problems, and from 1960s onward, aerospace industries has integrated CFD techniques in design and R&D and manufacturing of aircraft and the jet engines. So, they are using for a long time. Now, your own CFD coding and your commercial CFD codes. Okay. Yes, when I started doing my PhD, a lot of people actually told I am using some black box and I have no idea about what is solving this system, and these guys, they are so much negative until 2010, 2011. Lot of people, they are very negative about using the commercial software. Before that, as Professor Chakraborty told, that he developed his own code and those kind of things. But after that, what happened is, when you develop your own code, the geometry should be very simplified geometry. If it is a complex geometry like your lung tree, it is quite impossible using your own code. Okay? It's a very hard job. Like in your 3 to 4 years PhD, you have to use maybe 2 years or 3 years just to develop the code, and you will get only 1 year to do the application. So, and this CFD code, like the commercial code, it tested by so many people all over the world. So, that means this actually proved that it working perfectly. Or if it is your own code, maybe you can do some manipulation in your code, who knows. Okay? So, I think is reliability of using this software nowadays people actually realize, and now nobody will laugh if you use any these things. But it depends. If you are a mathematician, most of the mathematician they actually develop the code. They like to develop the code, and that's why we are getting this kind of software, because behind this developing this software, a lot of mathematicians are working. They are actually developing codes, and they are helping for this one, and now we are using it. So, it depends what is your goal, what you are going to do. Okay? If you want to do like develop your own new methodology, new technique, then you can just work on the code development. But if you want to apply your code to apply some engineering problems, okay, and to understand the physics, so you can use this commercial software. So, it actually depends. So, problem solving using commercial package. So, in the commercial package, we actually, it is very nicely organized because it is commercially, otherwise you won't buy it. Okay? So, there are some free or the open source like software, those are very good, like the Open Foam, they are very good, but they are not very user friendly. Okay? So, but they actually make very nice user friendly, and they put everything in one place. So, what they have is, they have like a preprocessor, a solver, and a post processor, everything is there. Okay? So, initially you thought about which problem you are going to solve, you calculate, you find out what will be the boundary condition, what will be the initial condition, what will be the geometry, you just think about it, this is called the preprocessor. And then you put everything and put in the solver, and it is solving. But after it is solving, what you want to do? You need to present the results. So, it is actually solving and storing data, all the nodal point. Okay? Professor already mentioned that in the node point, but if you want to get the result somewhere else, okay, in between nodes, so you need the interpolation. Okay? So, that is the things that the post processing software can do that for you. So, and Ansys Fluent or Ansys has its own CFD post, they call it CFD post. So, you can do the post processing there, or some other people use like a tech plot or some other third party software. So, you can also use it. And Fluent has its own post processing one, and Ansys has its own CFD post. There is a lot of way you can do it, but CFD post is very powerful, very nice. You can show a lot of things in there. So, the preprocessor actually this step includes the creating geometry and the mesh. Okay. So, thus creating geometry and the mesh you can use somewhere else, and you can export the mesh and put in the solver. So, this part is to numerically solve the fluid flow equations in the computational domain. Now, the post processor in these steps, results of simulation is analyzed and represented is usual form. So, which one you like, the way your manager or your supervisor wants, you can actually present the result that way. So, this is very nice tools. So, the three method. So, three method is mostly used. Okay. It is called the finite difference method. You already have learned what it is. And then the finite element method, which is not in this course, and the spectral method, not its code. But the finite volume method actually the special case of finite difference method. Okay. So, there are some special case. And this finite element and spectral methods we are not using it. There are also other methods like LBM, lattice Boltzmann method, the mesh free particle methods, a lot of methods are available. So, Ansys Fluent. So, Ansys is an engineering simulation software. Okay. So, is a developer headquartered south of Pittsburgh in the South Point Business Park in So, this is there where it is. So, Ansys Fluent is one of the most popular commercial CFD software package. So, we will use Ansys Fluent in this course to solve the engineering problem. Okay. So, the Ansys Fluent CFD solver based on the finite volume method I already mentioned you. So, in the finite volume method you know that the domain is discretized into a finite number of control volumes. Okay. So, the conservation equation of mass, the momentum and the energy if you have heat transfer related problem, and species if you have some diffusion problem. So, this kind of things are solved based on these control volumes. So, now the steps in Ansys Fluent, what steps we want to follow here, and at first the pre-analysis. Okay. So, as I said, what kind of problem you are going to solve, what could be the initial and the boundary condition. So, if you have anything everything handy, then you do the create the geometry. Okay. Create the geometry you can use any CAD software, but to use in that software in Ansys Fluent, I think you need to export the geometry into IGES format. Okay. So, start.IGES. So, this format you have to export, and then you can take it directly to the Fluent. And then you have to apply the mesh. Okay. So, Ansys has very nice meshing technique. So, there are three things in Ansys Fluent. Okay. Is before you go to Fluent, there are in Ansys you can say as a general. So, the geometry creation we have the ICME I think is ICEM sorry ICEM. So, you can create the geometry in ICEM, and then now we have it's called discovery something, right. There is newly they release another one is called Ansys discovery or something. So, that is a very close to the like the SolidWorks. Okay. You can actually create the geometry there, or you can use the Ansys' own geometry. There you can also do that. So, once you create the geometry, is just bring the geometry to the mesh. Okay. And then you apply the mesh. So, mesh also has ICEM can give you, that is very good for the hexa mesh or rectangular mesh or square mesh. Okay, that is very good. But if you have very complex mesh like a tetrahedral mesh or some other mesh, I think the Ansys meshing system can do that. And after that you need to do the physical setup. Okay. Set up all the boundary conditions and or like everything like a model choose. There are a lot of models there. Which model you want to choose? Okay. Because we discuss only the simple one. There are some other solver there and lot of other things as well. So, we will show you when we, this afternoon we will show you. We can show all the possibilities, and also Ansys Fluent give us a recommendation what kind of problem you should use which one, but you can do some testing, and then you can do the numerical solution, and after that do the verification and the validation. Okay. So, the best part of I like in Ansys is called the workbench. Workbench is like this kind of connections. They connect everything in one place. Okay. In Ansys workbench, you can just set up the circuit, and then from there you can just go for the geometry creation, finish the geometry, save it and come back, and then go for the meshing. The meshing can automatically get the geometry from there, and then you do the meshing. You just give all the boundary names, okay, and come back and then go to the Fluent. Fluent can automatically take the mesh file from there. You don't need to do anything. And if you want to do some optimization, So, you can also do the optimization in there. So, you can just you need to set up which parameter you want to optimize. So, just mention the parameters and that can actually optimize you. And after that, if you want to do the post processing using CFD post, then click the CFD post, they can take all the results from the fluent you already calculated. So, it is a fantastic way of doing using Workbench. You do not need to like do all these components, because all are separated, geometry is separate, then you can do meshing separate, and then you set up and then you run, all are actually separate files. But the Ansys Workbench actually is connecting everything together. So, it is a very nice tool. So, yeah, the Workbench looks like this. Okay. So, it has see on the left side, it can actually do a lot of things, but I never use this thing. This is some of them only for solid mechanics. Okay. We need only the fluid flow fluent and the fluid flow CFX. So, you can use either of these, both actually deal with the fluid. Okay. So, once you click on the fluid flow fluent, it actually gives this circuit, okay, like a geometry, the mesh, the setup, solution and the results. The results mean the CFD post. You will get everything in one place. Or the thing is that if you want to change anything anywhere, that actually influence everything. So, if you are very smart, you can take some component, not the all of this here. There are some component in the I think you have to go down. I could not show all here. So, this geometry, mesh, setup, solution, all are different components. So, you can just put on the geometry and then you can connect. Okay. You can connect geometry with the mesh in one, with the mesh other one, and the mesh on the third one. So, you can put lot of things together. If you change one, that will not alter your whole things. So, if you want to show some parametric study, okay, the couple of mesh you want to do, so this kind of thing. So, you can actually do that. We will show you when we this afternoon. Okay. So, this we will use this Ansys. Here is the tools of simulation using Ansys. You will use and control these tools from here. Okay. And here are all the tools you need for your simulation. So, geometry, click the geometry, it will open up the geometry page, or if you do it in ICEM or the discovery, you can actually export, right click and export the geometry. Okay. They will automatically open a new page. And then the mesh, then click mesh, it will open up the geometry, or if you have your own mesh, you just directly go to the setup. Okay. When you go to the setup, you can import the mesh file if you have. Okay. And then go to the solution, and after that the results. So, steps. So, the pre-analysis, you want to solve a real world engineering problem numerically using Ansys Fluent. Then you will need the boundary condition. As I said, boundary condition is very important. If your boundary condition is not realistic, you will not get good results. You will not solving the realistic condition. So, boundary condition is very accurately you have to deal with it. Otherwise, your result is not like a physically correct. So, you observe that the real physical situation, or you will obtain data so that you can represent the actual case. Okay. So, you will also obtain the corresponding theoretical or some experimental result, and then you can compare your results with them. So, in our CFD research, what we do is for the validation, for example, we are solving one problem, totally new problems. So, that problems is not solved yet, is not available. So, how can you validate? So, once you before you need to for the validation, so you have to actually get very similar or close to your problem, maybe someone already did. Okay. Just get their information and you just set up based on their data and get the results and then compare it. Once you compare means your solver, the solver issues and the setup you did is okay, is correct. Okay, that is the way we actually validate, because we do not if somebody already have done and then we do not need to do it again. Okay. So, you cannot exactly get some results already published and you compare your results. So, what you have to do, you have to actually design something already available in the literature and then get some results and compare with them, or if already available as an experimental data, so you do a numerical simulation based on the parameter they use, everything they use, and then compare your results. Okay. In that way, you can validate your model. So, a lot of way of the validation, and the Professor Chakraborty told that there is an upper limit and a lower limit of acceptance. So, if you want to know generally as a CFD researcher, what you do is generally if we compare our result with some numerical results, we just take the error like about 2% maximum. If the error is less than 2%, we accept. But if we compare our result with some experimental data, we can accept up to 10 to 15% error, because as I told, the experimental is a very uncertainty there, because it has some other influence from the environment. So, we still we just accept it. And sometimes, for example, our research, my group is doing lung. So, everybody lung are different, then how can we validate our model? Even though if I take a CT scan now and after a certain time, two results will be different, because I do not know where your diaphragm is, maybe your diaphragm coming here. So, you are taking different times, your geometry is different. So, there are a lot of issue previously from the reviewer, we get a lot of comments that how can you validate your model? It is not absolutely way of validating it. So, normally what we do, we just do not the very quantitatively, but qualitatively. Okay? It's just we calculate something, and already some people did, and we found that they are very like trained the same. Okay? Trained the same, this is the way we just validate. And we do a lot of mesh dependent tests, so that our mesh or our grid is not affecting our results. Okay. So, I already have mentioned it, the geometry, you need to create the geometry either using your Ansys design modeler software, or you can some CAD software, okay, and export that on as IGES format. And meshing is one of the most important step for your simulation, and the simulation result actually depend mesh quality. As I said, the more mesh you have, the better result you have, but we have to sometimes compromise, because we cannot use huge mesh. To solve our one lung problem, we use up to 30 million mesh. So, it takes about 1 month using 64 processor, 64 computer to solve one problem. It takes more than a month. So, sometimes it is not possible, not feasible. Okay. Now, then the physical setup. So, yeah, this is another important thing. So, Fluent already give some advice which type of model, like a natural convection, what kind of solver you need to use. So, what kind of discretization you need to use. So, they already give some idea, or you can do by yourself, do different testing and these things. But remember, in CFD, good results depend on your experience. Okay. So, do again, and then you will get your experience. What is the problem? Where is the problem? Then you can identify by yourself. Okay. So, now how to set it up? Just go to the Ansys workbench, and then the analysis systems, and then the Fluent Policy. Drag it, put it there and drag it there, and then you can see the Fluent solver using this path. Fluent tree will appear. This looks like, though this tree actually showing all the steps you have to complete for a successful simulations. Okay. So, first one is this one. When you just come to the Fluent, when you click the workbench, okay, is open up this one. So, once it is open up, then you have to think about what dimension your geometry is. Is it 2D or a 3D? So, if you choose if it is a 2D and you are choosing 3D, you cannot read. So, your geometry Fluent cannot read your geometry on your mesh file. So, you have to choose correct one, and but that one is if you use Workbench, that automatically they select, because they can recognize what is your geometry. If it is 2 dimensional, there is, it will be 2D select. And the double precision, and here you can tick or untick, it depends on you. So, how much correct results you want. Professor told yesterday the truncation error and some other error. So, this error is the precision error, that means after decimal places how long you want to keep your result correct. So, single position is 16 and double is 32. Okay. So, 32 is the huge, and it takes lot of space, the data file will be very big. Okay. And but generally I use this one because that will give you more accurate results, but it takes lot of your space, the file will be bigger. Okay. And now what you want to display here, displays the mesh after reading. So, when you go up give OK, that it can read your mesh file, and yeah, you can show which one you want, just tick here. And now the processing options. Do you want to use the serial or parallel computing? Okay. So, here you have to choose. If it is serial, that is one processor will solve your problem. So, nowadays the computer has 8 core, 4 core. Okay. So, you can even in your single computer you can use the parallel. You can use 4 or you can use 8 or something from here. So, that they can solve it very faster than the serial. Okay. So, here you have specify your solver about your geometry 2D or 3D, and the accuracy 1 like the tick, the double precision or the single precision, which one you want, and then unmark the double precision marks if your solver is single one, or you just mark it for the either see the 16-bit floating points, or double precision is giving 32-bit floating points. So, the processing options are to speed up your simulation and using full power of your cluster computer. So, you can use 1 core, or you can use some computer has some 8 cores. So, you can just select which one you want, or you can do some testing, because during my PhD my supervisor was very angry on me because I am using the maximum number of core, and then he said that you need to do some testing. So, which one is optimized? You know, sometimes parallel computing, if you use more processor, sometimes it will slow down, because it is called the message passing. So, one processor will pass the message to the other one. So, it takes some time. Okay. So, if you use more processor, it takes some time to pass the results, because it is called the domain decomposition. So, they are dividing the domain and solving one processor this part, other processor this part, and they are exchanging the value. So, to exchange the value, it takes some time. For example, maybe 4 processor is good for you, but if you use 8 processor, it takes time for this message passing and it slow down your these things. So, in that way he just told me do like simulate 10 iteration and see your real time how much it takes for single processor, then double processor how much time it takes, and draw a curve, and then curve is converged, take this one. Okay. This how many processor you need. So, that is very important. So, it is not always good to use like a maximum number of CPU. Okay. So, this is the Fluent. When you read a mesh file, it looks like that. Okay. Looks like this. So, the geometry they show the mesh here. Okay. And they will give all the information here, all the information, especially the mesh, all the mesh information you can see from here. Okay. So, you have to check very carefully that the volume of the mesh is not negative. So, there are sometimes if you have some error, it can give you some negative. So, we have to check it, and all the left panel you have to like choose for the solver and what kind of discretization need to use, everything on the left side. So, you have to do it. Okay. So, some of those things are very straightforward and some of these are not very straightforward. In that case, for example, like your boundary condition, if you want to give like some value like a temperature, like for example 300 Kelvin you want to put in one place, it is very easy, you can put it there. And or some flux condition, if you want to give like some watt per second or something, you can put it there, that's easy. But if it is like some complex boundary condition, like for example I am using for my lung, I am using like a very realistic breathing pattern. Okay? It is not a sine function, but it looks like a sine function. So, we have a profile for this. So, how to use in there? It is very tough. You cannot directly put it there. So, then you have to write a user defined function. Okay? And that user defined function you cannot use like your own language. So, you have to rely on how Fluent is built on. Okay? So, Fluent has some built in things, some macro. So, you have to use some of this to write down the these things, but they have a guide for that, how to write the user defined function. So, if you have like a complex kind of problem, you have to work on it, especially the Fluent is given the main scheme. Okay? Generally when we use our own coding, the main scheme we generally do not touch the main scheme. Okay? We touch some other subroutine, okay, where you need to change. So, this kind of things we have to write a user defined function, means it is another subroutine we have to attach to it. And there are some other things like for example, if you want some heat generation somewhere inside the domain, we have to write that on as well. So, it is not very like a click, put and get the results, is not so easy. If your problem is complex, you have to deal with that way. So, these are the tabs. Okay. So, this is the, you calculate the run calculator, it start running it. So, these tabs allow you to describe your problems, physics and control your simulation. For this course, our current objective is to be familiar with these tabs. So, that will show you, know the details about them and use them for a successful simulation. Okay. I am just going very briefly. So, here we have another thing is like beginning of the Fluent. Okay. We have this kind of things, the mesh. So, you can check the mesh, click the check and then it will give you the all the mesh information. Okay. So, there you can check it and or you can display and you can see how the mesh looks like, and the solver. So, do you want to use the pressure based solver or density based solver? So, it actually depends. So, if it is like a high Mach number flow or like where the density changes, so you need to use the density based solver, otherwise mostly we use pressure based solver. Okay. And the velocity formulation is absolute or relative. So, we need to check it. And the time, are you solving for the steady state problem or the unsteady or the transient problem? That means del u del x of t, you are solving it or not. Because as I told you yesterday that most of the things in nature is steady state. Okay. So, if you want to use that one, just use the steady, or if you want to see the development of the flow or development of something from the beginning, you should use the transient one, and transient one is more complex and it needs a lot of time and also some analytical ability. Okay. And the 2D space, if you have like 2D problem, is it the axisymmetric case or planar case or this one. So, you have to choose from here, just take it there. And the gravity, do you need the gravity or not? Is your problem is related to some gravity? For example, if you want to solve some natural convection, okay. In natural convection there is no external force, like if you heat one surface, that heat can conduct through the wall and come inside and then hit the air, and air actually start to rise. So, that is called the buoyancy. So, that we have to give the gravity turn on. Even in our lung problem, we have to use the gravity, because the particle deposition sometimes is due to gravity. Okay. It goes, if it is heavier, it goes that way. So, we have to take it, but in some like microfluidics cases, generally they do not use gravity, because the gravity is neglected. It is very small cases, you do not need it. So, already I discussed, so I do not need to go this on. Now, here this is very important, what equations you are actually going to solve. So, there are a lot of equation here. The Professor Chakraborty already mentioned this morning. You can see the multi-phase. Your problem is multi-phase or single phase. So, you have to check it before you start. Okay. So, we are not dealing multi-phase here, we are dealing the single phase. So, that is op. Op means it is not activated for your problem. Now, energy, are you solving any temperature related problem? If it is, just double click and it will be on. Okay. And now, viscous, is it a laminar flow or turbulent flow? So, that is what I said, you need some experience. Okay. So, what kind of flow behavior you are expecting from this problem? Okay. If it is or there are some free calculation. For example, for a pipe flow, you already know that if the Reynolds number is less than 2000 or 2300, so it is a laminar flow. So, you can easily choose this viscous or laminar, or if it is more than 4000, it is a turbulent flow, then you can use viscous. There are some turbulent modeling. So, in turbulent flow there are a lot of model. Okay. There are LES, there are K epsilon, K omega, lot of things. So, you can actually choose one of them from here. Okay. And then radiation, is your problem related to any radiation, then you have to turn it on, and radiation has also 4 different kinds of radiation. Okay. Surface to surface. So, those kind of things. So, you can choose which one is appropriate for your model. So, that means you need some understanding before you solve a problem. It is not like you ticked on and get the results. Okay. You should have some knowledge beforehand which one will give you good results. Are you using the heat exchanger? You have to tick it on, or are you solving any species, any concentration related problem like a diffusion problem? You have to tick this on. Are you solving any discrete phase, or you are doing any solidification or melting? So, my group is working on phase change material. So, phase change material means is a solid phase and then is becoming liquid where the temperature comes. Okay. So, this time we need to turn on the solidification and melting. Okay. Mostly it is called a thermodynamics problem, and acoustics, are you doing it or not. So, those are very important, and you have to check all equations are different. So, which equations you are going to solve, and the good thing is that if you install the Ansys properly, everywhere in the bottom there is called help. If you click the help, it will show you all the explanation on everything, the things I already mentioned here, everything is there, and there are some recommendation. Okay, which one is for what. So, if you print it out, it will be like this kind of thick book. Okay. So, it is good that it is already in there, and it is like a web based, or there are some PDF as well. So, you can have a look. Okay, I already mentioned this. Now, the models, which models you want to use? The viscous, I already have told you. Now, the material properties. Okay. So, which material you are going to use? So, in Ansys model, we have a library of materials. Okay. You can choose from there, or if you know your own properties, you can also just select something like air and click on it and change the properties according to your data. That okay. So, name does not matter. So, you can actually do it. So, this material property, you need the accurate material property, because I think here most of you are engineer, right. So, engineer they are very strict about the dimension and the property. I know it. I am not engineering background, but I know engineer, they are very strict with the dimension and the material property, but as a scientist they do not care about that. Okay. Scientists, they care about some parameters like the Reynolds number, Prandtl number, Rayleigh number. So, those kind of things actually generalized. Okay. All the dimension, all the parameters is going into that. So, now it does not matter is a very big room or a small room. If you just set of the parameter this, that actually represent everything. Okay. So, this is the difference between the engineer and the scientist. So, they make like this way. Okay. Here we have like a cell zone. So, you can check how many cell in your how many zones in your system, and this is the way you have to identify. Now, the boundary condition, as I told you, boundary condition you can have. So, generally we have here the inlet, the outlet and the wall condition, and the interior surface is nothing, just put it there. So, this wall boundary condition, so that means the wall is like a no slip boundary condition, that is the general, that is wall is not moving, but in some places we just move the wall. Okay. So, there are some way that you can specify the velocity on the wall can move. Also the inlet, you can put in the inlet, you can put like a velocity inlet, you can use like what I call is mass flow rate. Okay. So, anything you can put it there, and also apply the UDF, the user defined function, if your input inlet condition is complex, you have to write your own. So, the boundary condition I already mentioned. In the general pressure inlet, pressure outlet is mostly like an open condition. For example, in your lung we have like a 23 generation, but we can't actually get 23, we get about 15 to 17 generation. So, after that we just cut it and put it like a outlet condition. So, that means it is free, the particle and air can freely go. Okay. That is why it does not affect your anything, it is an open condition, we call it open boundary condition. In COMSOL they call it open boundary condition, in Ansys Fluent they call it pressure outlet condition. Okay. Now, for incompressible, because it is a compressible incompressible, we have the velocity inlet and the outflow. Yeah, like for compressible we have mass flow rate, mass flow inlet or pressure far field. For other wall we have symmetry. Okay. So, if your flow is symmetrical, for example, like a attic shape building, okay, attic shape building, the building roof is like that. So, initially it is thought that the flow is symmetric. So, the streamline like that is a half of this the same, this one is the mirror image of that one. So, in that case they did not solve the whole triangular shape, they put the half of the triangular, okay, right angle triangle, normally they solve this one, but later on they found that no, this is not right. So, sometimes the flow actually changes, is not symmetric, but yeah, this kind of symmetry condition you can use the symmetry boundary condition, axis boundary condition or some periodic, if like comes every interval the same results, you can apply the periodic boundary condition, okay, and it will be the same. Some special is called the inlet or outlet vent, intake or exhaust fan, this kind of boundary condition you can apply, and the internal one you can use some fan. Okay, we just do for the mixing, we use the fan internally. Some interior condition you need to do anything in there, some porous jam, radiator, wall, so this kind of condition. This is boundary condition, velocity inlet, you already have mentioned, I do not want to mention anymore. So, pressure outlet, all boundaries. Okay. And dynamic mesh, sometimes we need to like it is especially used for fluid structure interaction. Okay. We need a moving mesh. For example, something is moving that way, and we know that close to this solid one is very sensitive. So, we need to give like a very dense mesh near the solid wall. Okay. So, that is why if we move that way and if your mesh is here, the highest mesh, it does not work. So, that is why mesh should also move with this geometry. Okay. That is how we need a moving mesh, but in your case we are not showing it. And the reference value. So, reference value does not do anything with your simulation, but actually it help you for the post processing. Okay. Post processing means, for example, when you calculate the Nusselt number or the heat transfer rate. Okay. So, in that case you need a reference temperature. So, if your reference temperature is not correct, which reference temperature you are calculating your Nusselt number, then you will not get correct results. So, for example, if it is a time dependent one, okay, from 1 to 10 seconds, and you want to get a curve, and then every time step it is calculating the Nusselt number, but if the temperature is not correct, it is not giving you the correct solution. Okay. So, that is why it is also the reference value is also important for your post processing. It does not do anything with your results, with your simulation. I think that is it. And solution method. Okay. Yeah, sorry, we forget the solution method. Yeah, here we mentioned that for solution method we have the pressure velocity coupling. Okay. So, you see the pressure velocity coupling in the momentum equation, you see the pressure on the right side minus 1 by rho del P del x. So, that is called the pressure gradient. So, that one we there are scheme we use simple scheme. There are some simple egg, there are some it's called Pichot or something. There are a lot of scheme there. So, you have to select which one you want, and then for the special discretization we have least square cell based, okay, or you can use like the quick scheme, okay, or second order upwind or first order. First order is very simple. So, for the pressure discretization, for momentum discretization, it is the default is second order upwind, but you can use like the quick scheme as well, QUICK, quick scheme. So, the simple method is very popular and widely used. So, we will use here this simple method, and coupled method is also popular and helps in convergence. Yeah, so, if simple one is giving you divergence your results, choose the couple one. Okay. So, you can choose one of these. Now, these are the things yesterday Professor Chakraborty told about your the relaxation factor, okay, for your quick convergency. So, these are the important things for pressure term, for the density, for body force and for momentum. So, these are the value. One is default. So, that means the density and body force does not actually interfere for your convergency, but the most problem is the pressure, the continuity equation. Okay. So, you can see the white line, it does not come down your residual. So, we normally set up some residual value, the default value is 10 to the power minus 3, but if you make it smaller 10 to the power minus 5 or something, you can see the pressure or the continuity equation is not coming down, it takes long time to come down, or sometimes it does not come down, goes up. So, diverge your solution. So, that is why you see very small value, use 0.3, okay, we just generally do it, and if you put too much small it takes long time, but we do not know, we have to just try. So, this is the default value. If your solution does not converge, just try to reduce it, okay, and you can try it. Generally these are the default value. Yeah, this is the residual. So, generally for continuity, x velocity, y velocity, energy, everything, the default value is 10 to the power minus 3, but here you can see 10 to the minus 6. So, it is up to you how much accurate you see your results, but remember if you give more value, smaller this, it takes longer time for the simulation. Okay. What else here? Yeah, and what you want to see on the screen on the left side, you can tick print to the console, that means in the bottom they can just print it, and plot means if you tick the plot they will show graphically. So, the solution control, these are the things I already told you. Yeah, initialization. So, you have to give some initial value, and every time you run a simulation you have to do the initialization. There are two ways of doing the initialization. One is called the standard initialization, you put all the values, and another called the hybrid initialization. You don't need to do it, just click it. It will actually do it all together, initialize your system and then start the simulation. And calculation activity here, if you want to do some animation at the end, so you have to like modify how you want to save the data. Okay. So, if it is a time dependent problem, then maybe after every 50 time step or 10 time step or 100 time step, you want to save your data, and at the end you can create the animation. You see how the fluid is flowing. So, you can see at the end. So, this is the place where you can specify how many, because you cannot save the data for every time step. If your time step is thousands or hundreds of thousands, you cannot do that. It will take lot of space. Okay. But this is the way you just find out some reasonable number, and that is the way you just do it. And then run the calculation. So, for a steady state problem, you only need to give the number of iteration, how many iteration you want. Okay. So, for example, we just give 1000 iteration and you found that the solution does not converge. Does not converge means it is not coming down the residual value. We already set up the residual value, and you can see it is coming up to here and 1000 finished. So, you can increase the number again and click. Do not click the initialization again, then you will start from the beginning. Okay. So, you can increase 1000 again, and you can see it is coming down, and after a certain time it is just finished, and then you give the converge solution, and then you can do the post processing. Yeah. After that is the post processing, and we will show you how to do the post processing. Okay. This is a CFD post. Okay. So, you just click on the results, solution already did, click the results, and then it will go the CFD post. That is it. Thank you. Do you have any question? If you have no question, then maybe